Okay. Ladies and gentlemen, I had the pleasure to open this academic session. Now I have the duty to close it. We had a lot of scientific information, nice and interesting, very dense scientific presentations, and sometimes there were small messages slipping in these presentations. And so I thought that now, at the end of this session, I would wrap up some of the messages and some of the as conclusions of these 50 years of work at the Agronomy Institute, and also give you some ideas about the perspectives that we have for the future. So, a very important thing that maybe has not been made so clear, but which is true, is that the Institute has grown remarkably over the last 50 years. It has grown in size. The number of staff has increased by about a factor of 3. It has grown in budget, and it has grown also in diversity of topics. And so we can wonder, what are the key elements of our attitude and of our environment that have influenced this growth? And that's what I want to express in this talk. I put together a number of keywords that I think are at the basis of our growth: scientific freedom, capacity, flexibility, adaptation, dynamism, technology, continuity, quality, and partnership. And I will go through each of these words and explain you a little bit what I mean behind these. Dynamism. Dynamism goes together also with flexibility and adaptation. The growth of BIRA has been achieved almost only through external project funding. And to get that, it requires a very dynamic staff. It requires also that people and scientists and all the staff adapt to national and international research programs. We are living in a changing research environment, and as you heard already in the talk from Guy Brasseur and the next talks, we started with very fundamental research, mainly in the upper atmosphere, and we came down to the troposphere. Now we are faced with climate. So the research environment has changed. National and international programs adapt to that, and also we have had to adapt to these changing conditions. This requires also some flexibility in the management of the Institute. Staff had some skills, as we heard, calculators in the beginning, then they had to get used to computers, so people had to adapt to that and flexibly managed by the directors of the Institute. At the same time, if you want to get external project funding, you have to keep a high level of competitivity. You are, of course, not alone on the world, and there are many other institutes trying to get funding, so you must be excellent and keep a level of competitivity. At this moment, at the end of 2013 or now, the ratio of our dotation, so the money that we get for our functioning from the federal state through BELSPO, the ratio of this dotation to our external funding is in the ratio of 1:7. And only 30% of our personnel is statutory. So this shows you how dynamic we have been and still are, but it also shows that we are a little bit fragile. We are very much dependent on this external funding, and because it is external funding, it's mainly linked to programmed research. So we are quite linked to programmed research, which might limit our freedom. Another very practical implication of this growth is that the staff had to adapt to the local working conditions. And from the very comfortable situation in the early 1980s, where one person had an office on its own, we started to put 2 people in one room, and now we are in the situation where we have 4 scientists sharing one office. And this sometimes creates not the most comfortable conditions for working. And the Institute, which looked like this in the early years, now rather looks like this. Another element of BIRA's growth is its capacity. Its capacity, which has come through partnerships and also to continuity. It is important to develop capacity by diversifying your science domains. And we have mainly diversified the applied science domains. Our main skills are still the same. We are physicists, chemists, engineers, mathematicians, but we have gone into different applied directions. And to do that, you have to hire adequately trained people, and you don't not always find them in Belgium. So we have also, as it was shown already by Jean-Claude Gérard in the beginning, you have to go international, which is not always very much supported by Belgian law. It's also so that in Belgian universities, education, a specific education in aeronomy, is still very poor or almost missing. And so we have also, as already Johan also told you, we contribute to education in space sciences and environmental sciences in Belgium to attract young people in our domain and to get PhD students that can work with us together and get trained on the field. Even if we have grown, we are still, especially on the international scene, still a quite small organization. And so it is important to build partnerships, structural partnerships. We have some, for example, with KU Leuven, with UCL, and also ad hoc partnerships at the international level. We also have structural partnerships at the international level, like it was mentioned several times with the Service d'Aéronomie, which is now LATMOS, or with the KNMI in the Netherlands, for example. And this is especially important for space missions, where we also have important partnerships with industries and space agencies. And it is especially important also for tackling topics like climate change, which have a very wide scope and a socio-economic impact, and where we don't have all the skills in-house to address the complete issues. Once you have developed capacity, you have to maintain it. And to maintain your capacity, you need some funding continuity at a certain base level. It is very well to have projects, but if you don't have a stable, continuous funding, you cannot maintain your capacity. People go away and you lose expertise. And this continuity at a certain base level is especially important for space missions. They are typically lasting more than 10 years, so you really need a team which continues accompanying the space missions. In between missions, you sometimes have gaps, and so to fill these gaps, you must be able to maintain your team and your expertise. And if you want to get into new missions, you have to prepare them, and you have to prepare them before there are dedicated projects for these missions. So you need some basic funding. You need also to maintain your capacity at a monitoring level. We heard several times the importance of long-term monitoring, and it is very much linked to our basic mission to study global changes. And this requires also continuity. It's a very important aspect of our mission because it is linked to the need to support environmental policies with objective scientific information. And just to illustrate the importance of continuity, you have seen this time series of stratospheric BRO in Norway, taken by our institute since the end of the 1990s, where you see really the upward trend in the end of the 90s and then the decreasing trend in the years 2000 due to the regulations of the Montreal Protocol. If we had interrupted the time series for a few years, we would completely have missed the maximum and we would have had a very different trend. So it's very important to be continuous in your measurements. Another important element is scientific freedom. We have already heard several times that it's important to have, next to the applied research, to be able to continue fundamental research. And it's also important, as it was also said already by Jean-Claude Gérard, to be able to do some new science, exploratory science, pioneering research. And for example, the planets and the comets, there's no direct application, but it's very important to do that kind of research. We have to develop new observation techniques, to develop new capacities. Laboratory experiments are still very important. And so it is important to continue research which has not necessarily within a well-defined program. Scientists must have the freedom to develop new ideas. Even if they have not a direct societal relevance, and if there is a risk, maybe the outcome will not be what we expect or what we hope for. It is not predictable. And this is very important to grow and to stay at a level of competitivity. Another key element is quality and excellence. The quality of our research should be maintained. It is very important to enable reliable scientific information and scientific services to the society. And this requires quality at all levels of the research chain, from the data to the analysis of the data, to the information that you get out of it, and to the service. It also requires a continuous revision of your data and your analysis to keep up to date with current quality standards. It is well known that satellite data or ground-based data require regular reprocessing. Many years after the end of the mission, we are still reprocessing the data. They need to be harmonized from different satellites, and they need to be homogenized if you want to have reliable trends. And we have seen as an example the ozone climate change in program from ESA, where there is a lot of effort put into the homogenization of different time series from successive satellites. Technology, we heard in the previous talk the big importance of technology in our science. Progress in technology and aeronomy science go hand in hand. This is true for space instruments, where I think the actual tendency is to go from large satellites, which are very performant but complex, expensive, which require long preparation time and which imply also a large risk, to the more smaller satellites, even to the pico satellites, which are cheaper, simpler, faster in their development and smaller. And we have all seen the example of Picasso. Also in airborne and mobile ground-based instruments, there is a lot of progress in the technology. Miniaturization is really very important, and we developed, as it was also shown already by Michel, instruments that can be put onto a car where you can drive through the country to do air quality measurements. Or very small instruments, spectrometric remote sensing instruments that you can put on an unmanned airborne vehicle to do air quality measurements at a very local scale. NIT, we had a lot of examples before, so I will not go again into the details. Now, for the perspectives. Is aeronomy a science without future? No, surely not. We have heard many times that there are still many issues to be solved. And as always in science, if you solve a question, you raise new questions. And so there are still many scientific challenges ahead of us. And I will just give a few examples. It's not at all exhaustive. One of the scientific challenges that I see is the fact that we are moving from the global level to the regional and even the local level, but at the global scale. This picture shows you the evolution of the spatial resolution of satellite experiments from the level of 70 times 40 squared kilometers to 24 times 13 squared kilometers to 12 times 13 squared kilometers with OMI. And we heard already about TROPOMI, which will be the next generation, which resolutions of the order of 7 times 7 squared kilometers. And you see how the level of details increases and how the information that we can get from these satellites increases. Of course, this requires adapted technology, IT, enormous data storage, and also a very big challenge to process all these data on a near real-time scale. It requires adapted technology, but also adapted science. You need to develop models to interpret this data. You need to develop models that go down to the regional and the local scale, which implies new processes that you have to take into account, and so on. Sorry. Another very important scientific challenge, to my opinion, is to better understand the interactions and the feedbacks between the various Earth system components. And Jean-François alluded already to that. For example, the feedbacks between climate change and the biosphere changes. Also, as Michel pointed out, the ozone recovery in a changing climate. We will never return to the conditions before the ozone hole, because in the meantime, the climate has changed, and so all the conditions where ozone is processed in the atmosphere are changing. And there are very important links, radiative links between ozone and temperature. There are important links with the dynamics of the atmosphere, which has also changed under the influence of temperature. And if there is a large volcanic eruption, there is also some feedback with the aerosol, for example. So this is a very important topic, and many things are not known yet. And I took this picture from the WMO scientific assessment of ozone depletion of 2010, but I think the situation has not fundamentally changed now. Michel showed you the trend in ozone and the expected ozone recovery based on model projections with quite a large uncertainty on it. This picture shows you which are the main contributions to these uncertainties. So on the vertical scale, you have an estimate, a measure of the uncertainty on a model projection of ozone as a function of the future. And for different regions of the world, global, the tropics, the northern and the southern mid-latitudes, spring in the northern polar regions, and spring in the southern polar regions. And you see on this graph the total uncertainty in the black curve and the different contributions to this uncertainty. And the green curves are the contributions to the uncertainty due to the unknown scenarios for the greenhouse gas changes. And you see that as further as we go in time, of course, these uncertainties become larger. But you see that the blue curve gives you the uncertainties due to different models. So different models implement the different processes in the atmosphere in a different way, or some models implement some processes and some others not. And so you see that the total uncertainty is still dominated, in fact, by the uncertainty due to the models themselves. And this is with the models that we know, but we know already that many processes are not yet implemented in the models, like the interactions between the oceans, the climate, the cryosphere, and the atmosphere. So there is still a lot of work to do to improve the models and to understand all the processes. So, as I said, the model uncertainties are the largest contribution to the total uncertainty, especially in the first half of the century. And several processes are still missing, and we have to study them. Another, of course, important scientific challenge is to further explore the planetary system, in particular the atmospheres of more distant or giant planets like Jupiter or the exoplanets. And we know that all the planets have very different atmosphere, very different magnetic conditions, and so there is still a lot of fundamental research to be done in this area. The Institute will probably look different also in 50 years from now, and it is very difficult to make projections over 50 years, as we have seen in 50 years how we have changed in the past 50 years. I don't want to make projections for the future, but there are probably also some organizational and some institutional challenges ahead of us. What I see as, for example, challenges for the Institute are the technological progress, which requires ever more specialization. For example, high-performance computing specialists, electronic specialties like field programmable gate arrays and things like that. Maybe we will also evolve to a more multidisciplinary environment. If you see all the feedbacks that we have to solve, it is, of course, we can do that through partnerships, but probably we will also evolve into a more multidisciplinary environment. We always need to work faster, cheaper, because the society wants the information always at a faster pace. And then, for example, e-administration was mentioned. We are working very hard on getting rid of paperwork and putting everything into the digital form, with the help, of course, from our IT department. The immediate challenge is our working environment at the moment. Just now, we have had the chance to have some renovated offices and a new meeting room, Salle Nicolet. This is our new renovated offices and a new meeting room. And we are very thankful to the Régie der Gebouwen, the Régie des Bâtiments, to have supported these renovations. Also, of course, to the people from the Institute itself who supported all these works. But still, there is a very poor situation of our mechanical workshop. It is really degraded, and we are waiting very much for the modern building that was promised to us, accommodating our present needs, and we hope that these plans will be realized in 2015. So we are confident that we are well equipped to face the challenges of the future with confidence and aim for excellence. And I invite you also to go to our website, which is mentioned here, aeronomy.be, where we have some dedicated web pages dedicated to our 50th anniversary, and where you can still find a lot of historical material and actual material of our present situation. And I thank you for your attention.